So this is number 31. Which of the following is acidic? So deciding whether it's acidic or basic makes you take each one of these and break it up into its ions. And so, for example, for letter A, you'd have a K plus ion and an NO3 minus ion. And this is one of the most simple ones to tell whether it's acidic, basic, or neutral, because what you ask is, where did this come from? Did it come from a strong acid or a strong base? And where did this come from? Did it come from a strong acid or a strong base? The cations would always come from strong bases. The anions would always come from strong acids. And if they both came from strongs, they have no affinity to get an H, and they don't have an H to give away. And so they can't be an acid and they can't be a base. So this would be negligible or not acidic or basic. Now the problem comes in when you have something that is from a weak acid or a weak base. Like, for example, letter E right here. You'll have Na plus, 3 of them actually, and then you'll have PO43 minus. This, of course, came from a strong base, because if you look on your periodic table, it came from the B right here, and those are the strong bases. So that's going to do nothing in solution. But this one did not come from a strong acid, and therefore this thing is okay with getting some H's. It's going to want to get an H to become a little bit more like its former weak acid. And so this thing could act basic. And so always ask yourself, where did it come from? Did it come from a strong? If it did, it will do nothing. If it came from a weak, then it has an affinity to get back to be like that former self, if it can be. And so in this case, which one could be acidic? Let's look at letter B right here, and you can see that we have NH4 plus and Cl minus. Well, Cl minus, of course, came from Hydrohickel high, so that came from a strong acid, so that'll do nothing. But this guy right here has a spare hydrogen, and if it could, it wouldn't mind giving away one of these hydrogens and then becoming NH3, which you might or might not know is a weak base. And so it's okay with giving up a hydrogen, not a lot of hydrogens, but a little bit of one, and so this is weakly acidic. And this is a good example of a cation right here that did not come from a strong base, it came from a weak base. How do I know it's a weak base? Well, because it's not one of the strong ones. That's how I know. So anyway, this one would be our answer for which one could be acidic. Letter B is in Bob. Which of the following are basic? Hint, think Bronsted-Lowry. So a basic one would be one that would be willing to get a proton. So look right here in letter E, break it up. We know that we've got Li plus and we've got some C2H3O2 minus. So this would be from a weak acid, it would be good at getting protons and becoming the weak acid HC2H3O2, which is known as acetic acid. And so this one would act basic and would be a good getter of protons. All right, on to chapter 20 and some redox questions. Which is the oxidation number of sulfur in H2SO4? So hydrogen is always +1, oxygen is always -2. Doing some math in here, +1 times 2 for the hydrogen plus whatever sulfur is, plus oxygen is always -2 times 4, and the whole thing's got to add up to whatever charge is in the upper right-hand corner, and there's no charge, so it's got to add up to 0. That means sulfur here's got to be, +6. So that'd be number A right here. Which of the following metals can be oxidized by a strong acid? Why? So to find that out, you're going to need the E sheet. You're going to need the standard reduction potentials sheet. And so you want to know which one could have more of a possibility of being oxidized, therefore have a lower number than what the strong acid's oxidation number would be. Now, there's not going to be one of these questions on the pandemic year, so I'm going to skip it for right now, but just so you know, in case you're watching this in future years, you'd be given a sheet that has the E values right here, the standard reduction potentials, and then they'd be given in order, and they'd have H plus in there right in the middle, and then you'd look above and below, and the ones that are below that could be oxidized, because remember it's always listed as reduction, could be the ones that could be oxidized by. Number 35, which of the following can be oxidized by iodine? This is the same type of thing. So then you'd have to look up iodine on that list and then decide whether the substances here would be below it. Number 36, blank is the oxidizing agent, aka the substance is reduced in the reaction below. So to do this, you've got to go through and assign oxidation numbers. So oxygen is -2. Chlorine in this case then would have to be +7. Iron right here is +2. This is +1. Over here on this side, the chlorine's -1 and iron's +3. So I can see that iron went from 2 to 3, so it went up in charge and it is oxidized, therefore it's the reducing agent. And we can see that chlorine went from 7 to 1, so it went down in charge, so it is reduced, therefore it is the oxidizing agent. And so the oxidizing agent is the Cl-4- species here on this side. What is the standard EMF for the following reaction? So to be able to do this one, we've got to have a standard reduction potentials chart right here in E sheet once again. And I think on most tests they'd probably be given to you rather than a big huge sheet. But I'll look these up really quick and then we'll do the math here. So E, remember, is equal to the cathode minus the anode. And so to decide which one is the cathode and the anode, you've got to assign oxidation numbers. And then once you assign oxidation numbers, you have to decide which thing is oxidized and which thing is reduced. And of course, the anode is the one that's oxidized, and the red cat is the one that's reduced. So the cathode is the one that's reduced. So zinc starts here at 0, oxygen starts here at 0, hydrogen is +1. Over here, zinc is +2. Over here, oxygen is -2. So you can see that zinc goes up, therefore it's oxidized, and so it's the anode. And then you can see oxygen goes from 0 to -2, and so it is reduced. It is the cathode. So we'll do cathode minus anode right here. So our cathode is our oxygen, so we need to find oxygen on here. And this is pretty small, so I'll see if I can find it. We have to find the oxygen right here. Okay, 1.23. Okay, and this is oxygen in its molecular species right here. And then the anode would be the zinc. So we've got to find zinc, and that should be alphabetical down here, so way here at the bottom. And the zinc is -0.763. -0.763. So now we're going to end up adding those. So we're going to get pretty close to 2. And so the one that's pretty close to 2, I believe, is this +1.99 volts right here. All right. Then on this page right here, at least this year, it will be in the academic future. And then we're on to these guys right here, number 44 and 45. A reaction has an activation energy of 40 kilojoules per mole and an overall energy change of -100 kilojoules per mole. In each of the potential energy diagrams shown below, the horizontal axis is the reaction coordinate and the vertical axis is the potential energy. Which potential energy diagram best describes this reaction? So I always think before you look at one of these, you try to draw it on your own. And so if you draw it on your own, we've got potential energy right here, and we've got the reaction's progress right here. And it says it has a positive activation energy of 440 kilojoules. So wherever you start, you're going to have a hill that goes up 40. So this is going to have to go up 40. Okay? And then it says an overall energy change of -100 kilojoules. And so that means from the start right here to the end down here, you're going to have a difference of 100. I didn't space it out very good right here to make my scale very good. But you're going to have to end way down here. And so the difference right here between these two is 100 kilojoules per mole. Now it doesn't look the best because 100 would actually be like way down here with my scale being 40 right here. But we're going to have to find one that has a hill, and then it's going to have a valley down here. So I think we can find, here's one with a hill of 100, and then you can see right here that this would be the starting and ending would be 100 difference right here. So A is in aardvark. Number 45, what do a chemical indicator and buffer typically both contain? Well, a buffer is always a weak acid or base, and then its conjugate base, or its conjugate acid, based on what it is. So we got to find a weak acid and its conjugate base, which is letter D right here. Back with us more in the next video.